Okay, hi everybody. So today we have our fourth and final game theory lecture. So as I promised you last time, the topic of this lecture will be proving the min-max theorem that we formulated last time. So let me just say a few words about how the proof will go. So before we actually prove it, which will only be 2 slides, I'm going to tell you about a whole area of learning theory called no-regret learning. So this is going to be a very convoluted proof in the sense that you could prove the min-max theorem directly by linear algebra. It would be easier. You could prove it through LP duality, which we're not covering. There are many different proofs for this theorem. Most of them would be easier than the proof that we're going to do today. So why am I doing like this more convoluted proof? So the reason is that this area of learning theory, no-regret learning, I think is a really beautiful area. And I like theory, so from that viewpoint, it's really fun to see that area. But also, I think more importantly, AI is this really sprawling field. And even in this course, there's more focus than broader introductory AI courses. We still are covering quite a few topics. And at some points, they may seem to cover like a lot of ground. So I think when we have opportunities to really make connections between different areas of AI, we should really take that opportunity. And this is really an opportunity to make, I think, a really beautiful connection between this area of learning theory, no-regret learning, and game theory, which we just talked about for 3 lectures, which is really the basis of a lot of other work at the intersection of learning and games. Okay, so that's why I really want to tell you about this approach to thinking about the min-max theorem and proving it. So it's mostly about making the connection between these 2 areas. Okay, let me just remind you, we're going to get back to this at the end of this lecture, but let me just remind you of the statement of the min-max theorem. So we said, this was proved by von Neumann in 1928, and what it looks at is 2-player games that are zero-sum in the sense that the sum of the 2-player payoffs is 0. And we said, for every game like this, there is a unique value v, such that player 1, the row player, can guarantee at least a value of v, and player 2, the column player, can guarantee a loss of at most v, or guarantee player 1 a value of at most v. Right, so we were saying the payoffs in this game are the payoffs to player 1. Player 2 is trying to minimize these payoffs. So that was the statement of the min-max theorem. And last time we talked about its connection to, the connection of this min-max strategy to Nash equilibria. And also we talked about extensive form games that are zero-sum to make things a bit simpler. And like I said, what we'll do today is, for now, we'll forget about this theorem. I'm going to spend most of the lecture telling you about no-regret learning. And at the end of the lecture, we'll come back to the theorem and we'll prove it pretty easily using the stuff that we'll develop in this lecture. Okay, so using these learning theoretic tools. Okay, so for now, forget about game theory. We're going back to machine learning and talking about no-regret learning. So just to motivate this, here's one scenario you might think about. We're Bender the robot, as usual, and we're trying to reach our spaceship, Planet Express. And there are different routes we can take to work, represented by roads and intersections. So every morning, we need to pick one of n possible routes to work. And then we find out by listening to traffic reports how long every route took. So maybe, we take some route, and we take the red route maybe, and we find out it took us 53 minutes to reach work. But then we, by listening to traffic reports, we can maybe discover that if we took the blue route, this one, then that today would have taken 47 minutes instead of 53 minutes. Okay, so in that sense, we have a bit of regret for today not taking the blue route instead of the red route. Maybe that will make us think twice tomorrow about taking the red route instead of the blue route. So the question is there a strategy for picking routes that does almost as well as the best fixed route in hindsight? So this sounds like a very challenging thing to do, right? So what we're saying here is every morning we make a choice, and then we discover how good that choice was compared to other choices. And we're actually not going to make any assumptions about the structure of these losses. So it can be anything. And we discover these losses only after making the choice every morning. And what I'm asking here, which sounds impossible, is, if we knew in advance everything that would happen, the traffic on every day, would I be able to, choose a strategy that makes these decisions online, and yet is able to compete with what I could get if I chose the best thing in hindsight, when I know all of the traffic information, let's say for a month or for a year? So, that's a question where it sounds like the answer is no, but we'll see that the answer is essentially yes. So let's just, think about this in a slightly different way, a slightly more general way. So we can view this situation, this interaction between a player and an adversary as a matrix, where the algorithm is the row player, and every day the algorithm picks a row, and then the adversary every day picks a column. So this, so the row, you can think of it as a route. The column would be, if we think of each row as a route, the column would be what's the cost, how long it took to get to work on each one of these routes. What's the cost of each one of these strategies, or what's the loss? So what we get, if we chose this strategy, this route, and the adversary chose this payoff vector, then what we get is, the cost of taking this strategy, in face of what the adversary chose. But we also see the payoffs on the entire column. So we see how well every other strategy would have done if we had taken that strategy. Okay, is that clear? So you can think of the matrix shows payoffs, and you can think of it as the strategy decides on every day what's going to be the payoff or the loss or the cost of every possible strategy I could have taken. And then I find out what's the cost of my strategy, my action, but I also find out what's the cost of every possible action that I could have taken. Okay, and we're going to assume that the cost, yeah, Alex?
Every day matrix is different.
Okay, so the way I'm thinking about it here is every day the matrix is the same, and one way to think about it is the columns are all possible loss vectors that I could choose for the different actions, and then what the adversary does when it chooses a column is say, okay, these are the losses for today. So if you want like an infinite space of possible losses, you'd have an infinite number of columns. Okay, so it is the same matrix, it's just like a different choice of column on every day from this viewpoint. Yeah.
But is this sort of exhaustive if you want to find a loss for every single choice? Or is the loss in the third space comes from just looking one hop ahead? Or
So we are getting, we know the loss of every possible choice for the, for the current round after we make the choice. Okay, so we don't know the losses in the next round. We know for the current round after we make a choice. So we make a choice, and then the adversary reveals the column, which tells us the loss of our choice and every other choice. Okay, so I want to more formally, I was just saying like the costs we're assuming are going to be in 0, 1. Okay, so just a normalization assumption. Now let me define the question that I was asking before more rigorously. So I'm going to define the average regret in t time steps as the average per day cost of the algorithm minus the average per day cost of the best fixed row in hindsight. So another way to think about it is, after t rounds, I took a bunch of actions. I look at the best action in hindsight. I take the difference between my cost and the cost of that action, and I divide by the number of rounds t. Okay, so it's like the absolute difference in costs divided by the number of rounds, which is the same as saying it's the average, my average cost, minus the average cost of the best strategy in hindsight. Yeah.
So algorithm at every round could pick a different row.
Yes.
And then the best algorithm also can pick the different rows.
No. So what I'm competing with is the best single action in hindsight. So it's one single row. Yes. Yeah. So I mean, Alex is making a good point that an even stronger benchmark would be to compete with the best dynamic policy in hindsight that gets to choose a different action in every day. But that benchmark would be too difficult. Okay, so even like the benchmark that we're setting here, that's always already going to be quite non-trivial to compete with, and as we'll see, will be enough to prove the min-max theorem. This benchmark would be impossible to compete with. Okay, so this is again, just stressing this point again. This is this bullet point that we're not competing with an adaptive strategy. We're competing with a single fixed best row in hindsight. So our benchmark is not allowed to change strategies on every day. Okay, so what do we mean by a no-regret algorithm? It's an algorithm that guarantees, no matter what the adversary does, it guarantees that this average regret go to 0 as the number of rounds goes to infinity. So I'm suffering, I'm looking at the difference between me and the best fixed thing in hindsight, and this difference divided by the number of rounds is going to go to 0 as we play more and more. Okay, so this is saying, as we play more and more, I'm learning more and more about what the adversary is doing, and I regret less and less not having this information in advance. Okay, that's sort of the intuition what this is trying to capture.
So it's kind of in the end we want to discover that best fixed row, or not? If we discover it, then it will tend to 0.
Right.
Is that true? So we are going to discover that row.
Yeah, the thing is that we can never really discover it, because if we start playing the same row, the adversary can start giving bad costs to that row and good costs to other rows. So it's not really about discovering. If you looked in advance at what happens, then you could say it's about really discovering the fixed row. But when you take this online view, it's not about discovering anything, because then the adversary can mess with us when we start fixing our strategy. So it's more about balancing things out in a way that if the adversary wants to mess with us, he would have to make the best row worse than before. Right, so if we start playing that row, for example, in order for the adversary to make us suffer, he has to make that strategy suffer as well, and things sort of balance out. Okay, so I guess that would be the intuition. Okay, so let's start going through a few examples, and because this is really quite some definitions that are pretty difficult to digest. So we're going to start with some really simple cases and thinking about trying to design no-regret algorithms for these cases. So here's, just to get us started, a really simple example. So we just have two paths, two possible routes from home to work. So either going left or going right. And the adversary has two possible payoff vectors. So either he decides, let's actually call our strategies up and down to be consistent with the matrix. So either he decides that up gets a cost of 1 and down gets a cost of 0, or that up gets a cost of 0 and down gets a cost of 1. So actually, I'm even really restricting the possible costs the adversary can assign to the actions. Okay, these are the two possible cost vectors. And here's my algorithm. I'm just going to alternate between up and down. Okay, so on day 1 I choose up, on day 2 I choose down, on day 3 up, on day 4 down, and so on. So now, what I'm asking is, what is algorithm's one worst case average regret? So again, average regret is the regret per day, the difference between what the algorithm suffers and the cost of the optimal strategy in hindsight divided by the number of rounds. And when I say worst case, I mean if the adversary tries to mess with this particular algorithm as much as possible, what is this difference going to be? So that's poll number 1 on Piazza. Okay, quite nice. So we have almost half of you chose the right answer, which is theta of 1. I think maybe some of the people who chose theta of t are confused by the average versus the total regret. So let's just talk about this a bit. What would be a strategy for the adversary that would cause us to have theta of 1 average regret per round? Ankush?
Whenever we choose up, it chooses like 1, 0. Whenever we choose down.
Excellent, excellent. So Ankush is saying what we'll do is whenever we choose up, the adversary will choose a cost of 1 for up, 0 for down. Whenever we choose down, the adversary chooses a cost of 1 for down, 0 for up. So what happens is our cost, right, in every round, we suffer a cost of 1. And so let's look at our total cost, right? Our total cost will be t. Now, up suffers a cost of 1 every other round, and down suffers a cost of 1 every other round. So each one of them suffers a total cost of around t over 2. And then when we divide this by t, we get 1/2. Okay, so notice, by the way, for those who chose theta of t, I think it's the confusion about average. The average regret can never be more than 1 because the cost is 1 up to 1 per round, and then we're dividing by the number of rounds. So it can never be more than 1. It's just about remembering to divide by the number of rounds, which is why I left this option in this poll. Okay, so just don't get confused about the fact that we're asking about average regret, where we divide by the number of rounds. Okay, so is everybody okay with this? So we designed an adversary against this algorithm that causes it to have an average per round regret of 1/2. So this is not a no regret algorithm. The regret doesn't go to 0. Okay, so let's.
Like it will be true for any algorithm.
Yeah, we'll get there in a minute. So that's a very nice insight, but let's. We'll get to that in a few slides. Okay, good. So you already know the answer to this. So now I'm going to look at a slightly more clever algorithm. What I'll do is, every time in each round, the algorithm will choose an action that has a lower cost so far. So I look at the history. I don't know the future, but I look at the history, and I check which of the two actions, I can either choose up or down, which one of them has lower cost so far, and that's the action that I choose. Okay, so that seems to be a reasonable choice, right? Because I'm trying to go with something, like Alex was saying before, I'm sort of trying to find what's the best action in hindsight. A good guess for it would be the one that has lower cost so far. So let's try to go with that. So that's my algorithm. And the question is, again, the same question. What's going to be its worst case per round regret? So that's the real poll number 2 that now is actually called poll 2. Okay, 10 more seconds. Okay, excellent. So we have 60% for the right answer, which is theta of 1. So again, can somebody give me an adversary strategy that would lead to this relatively high regret?
choose the same strategy as before, alternate between giving 1, 0 and 0, 1, so that both have the same version cost.
Excellent. All right, so what Ankush is suggesting is, what we'll do is we'll just alternate between 1, 0 and 0, 1. So maybe in round 1, let's say we have up and down. In round 1, the adversary chooses 1 and 0. So let's say we played up. Let's do tie breaking. So we played up. The adversary chooses this. So now up has a cost of 1, down has a cost of 0. In the next round, we play down, and now the adversary plays 0, 1. So we again suffer a cost of 1. And now the two actions have the same cost. So we switch back to up. We play up. The adversary plays 1, 0, and so on. Yep.
In these cases, are the algorithm and adversary picking strategies at the same time, or is the adversary picking after?
Excellent. So Sherman is asking, like, is this a simultaneous move? And here, what's happening is the algorithm is deterministic. So basically, the adversary knows exactly what the algorithm will do at every step. So you could even think of it as like the adversary can choose the entire sequence of loss vectors or cost vectors in advance because it just knows exactly what's going to happen. And we're going to revisit this point later. Yeah, Ashwin.
You're saying the adversary doesn't make the decision after the algorithm makes the decision, but it knows what strategy the algorithm is using.
Right, so you can think of it for our current purposes as taking the action after the algorithm because then it knows exactly what the algorithm is going to do. It's a deterministic algorithm.
Yeah, but in a probabilistic algorithm,
Yeah.
you would just know what the algorithm is, but not look at the action and then.
Yeah, so we'll talk about randomized algorithms in a few minutes or in 30 minutes, and then it will know what the distribution is, but not what the realization is. Okay, great. So, so this particular strategy, just again for the adversary alternating between 0, 1 and 1, 0, we get the same thing. It causes the algorithm to mess up in every round. So every time we take the action that has a cost of 1. And again, we have the same situation where up and down, each one has an overall cost of t over 2, and then we get the same thing as before. Okay, but really the point I want to make, as some of you have already observed, is that this is a more general phenomenon. So we talked about two specific algorithms, and we showed how the algorithm can mess with both of them with a particular strategy for giving costs. But actually, the kind of thing we said can actually work for any deterministic algorithm. And the argument is as follows. So basically, what the adversary does, even in this case with only two actions, the adversary, for whatever action the algorithm chooses, it assigns a cost of 1 to that action and 0 to the other. Right? So again, we have the situation where the algorithm suffers a cost of 1 in every round, so its total cost is t. Now, if you think about the two actions, whatever we did, only one action in each round is getting a cost of 1, the other is getting a cost of 0. So we have two actions, their total cost is going to be t, and therefore one of them has to have a cost of at most t over 2. Right? One of them has to have a cost which is at most the average, and the average is t over 2. So this is a general argument. We're just saying, deterministic algorithm, the adversary always chooses the option that is bad for us and good for the other action. We always suffer a cost of 1. And just by this averaging argument, we can say of the two actions, one must have a cost of at most t over 2. And then we're again back to the same situation of a per round regret of at least 1/2. So what we proved is that actually for any deterministic algorithm, we can't deterministic algorithm will be a no-regret algorithm. Right? Any deterministic algorithm, even in a simple situation like this, with only 0, 1 cost and only two actions, we can always make it suffer linear regret over time. So the per round regret will be theta of 1. So what I want to do is sort of build our way towards using randomization to circumvent this problem. But on the way, we're going to look at some more deterministic algorithms, analyze them, and that will hopefully make the intuition for the randomized algorithm a bit easier. Okay, so to make things a bit nicer, we're going to stick to the simpler setting like we just had, where costs are either 0 or 1. And the way to think about it, which is one of the classic models that people have talked about in no-regret learning, is thinking about some prediction problem that you can get either right or wrong, and a set of experts. So the idea is that the experts are not necessarily true experts in terms of like getting stuff right, or just somebody with an opinion. So in this example, like our tasks are going to be to predict the stock market, and we're going to have 3 so-called experts, and the 4th will be my dog Charlie. And the way Charlie makes predictions is if his tail is pointing up, then he says yes, the stock market will go up, and if his tail is pointing down, then he says no, the stock market will go down. Okay, so on day 1, this is what happens. So expert 1 says will go down, expert 2 says go down, expert 3 says go up. We look at Charlie, his tail is pointing up, so Charlie is saying will go up. And the truth is that the stock market went up. So here, expert 3 and Charlie were correct, and experts 1 and 2 were wrong. Okay, now on day 2, expert 1 says up, expert 2 says down, expert 3 says up. We look at Charlie, his tail is pointing down, so Charlie says no, and the truth is no, so Charlie was correct again. And we just continue this process, okay? So, just to map this to our previous setting, here we think of the experts as the possible actions. These are the rows of our matrix. So we need to choose which expert to listen to. And then the costs are just 0 or 1. So if you got it right, you have a cost of 0, like an expert has a cost of 0. If the expert got it wrong, they have a cost of 1. And again, what we want to do, like before, is to do as well as the best expert in hindsight. Okay, so it's not going to be easy, but to start with a simple step, let's look at a simpler question. So instead of, we're going to change our goal and change our model, and what we'll say is, now there's actually one of the experts is an actual expert, he really knows what's going on, and this expert never makes a mistake. And our goal is to find out which of the experts is the one that is this perfect expert that never makes a mistake. So what our algorithm 3 is going to do is at every point keep track of which experts have never made a mistake, have always been correct so far. And we're going to take a majority vote over the experts that have been correct so far, and we'll do what the majority says. Right? And the question is, what is algorithm 3's worst case number of mistakes? So even as the number of rounds goes to infinity, I'm claiming there is going to be some bound on how many mistakes we could make overall by following this algorithm. And the question is, what's this bound going to be? Okay, so here there's actually a lot of disagreement. So there's almost a tie between theta of log n and theta of n. So let's actually do something that I don't do often. I want to give you guys some more time to think about this. So feel free to talk about it with others, and then you can change your vote, and we'll look again in a minute to see what happens. Okay, let's see what happens. Oh, oops, I'm offline, just a minute. Okay, excellent. So we do have now a nice majority for the right answer, which is log n. So would somebody like to say, what is the argument for why we can't make more than a logarithmic number of mistakes? Matthew?
Anytime you're wrong, over half the number of experts that are corrected for need to be wrong, then over half of them are no longer having been right all the time. So
Excellent.
you can only do that log n times.
Excellent. So Matthew is saying, the argument is every time we make a mistake, we basically get rid of at least half of the experts, right? Because we follow the majority opinion. If the majority misled us into making a mistake, that means half of the experts were wrong. So now we have a much better picture of which experts could be this perfect expert. We got rid of half of them. And after a logarithmic number of steps of getting rid of one half, we would only have one expert left, and then we would never make more mistakes. So this can only go on for log n steps of actually making mistakes. Okay, is everybody okay with this argument? Okay, so this is really nice. Right, this is really nice, but and it also leads us to something that gives us some guarantees, even in the setting where we don't have a perfect expert. So the idea is the following. We're going to, now we're back to our previous setting of listening to experts, and there's no perfect expert. But what we'll do is we just go with the majority opinion every time. Every time an expert makes a mistake, we cross them off the list, so we remove them from the pool of experts that we actually listen to. At some point, we'll probably end up in a situation where all of the experts make mistakes, and then we restart. Okay, so then we just put everybody back in our pool and restart the process. Now, the cool thing here is that still, in order for us to make a mistake, in order for us to make, to sort of finish a full cycle, so when we finish a full cycle, we know that each and every expert made at least one mistake. And by the same argument that we had before, we have made at most a logarithmic number of mistakes. Okay? So that means that we make at most log n mistakes per mistake of the best expert. Okay? Because we're forcing every expert to make a mistake for every logarithmic number of mistakes that we make. So this means that the number of mistakes we make is at most log n times the best expert in hindsight, which gives us something, but it's still very far from being a no-regret learning algorithm. Right? Even if we do twice as many as the best expert in hindsight, that's actually the situation we had here. That's not a no-regret learning algorithm. Okay? But still, at least it tells us, maybe this idea of listening to the majority is a good idea. Okay? And we want to take it further. And really, I mean, what seems really wasteful here is that every time we just restart from scratch. So we finish a whole cycle where everybody made mistakes, and then we completely forget about the history, put everybody, all of the experts, back in the pool. So actually, I added to the slide a slide that we had when we talked about tree search versus graph search. And we said with tree search, you sort of forget about the history and revisit nodes. And then I had like this quote this thought from Bender. So this is really relevant in many areas of AI and algorithms in general, and also relevant here. Right? It's really a mistake to forget about the history instead of using it to get better results. So I want to think about how to use the history in order to refine this idea of listening to the majority. So this is going to lead us to this really nice algorithm with a really, really beautiful analysis, the weighted majority algorithm. So one thing to note is this is still going to be a deterministic algorithm. So we still can't escape the problem that we talked about before. Okay? We're still stuck in the situation where we can't get no-regret learning algorithms because of the problem we talked about in the beginning of the lecture. But we'll be able to get a really nice bound, which is not a no-regret bound, but a really nice bound for this algorithm. And then we'll see how to adapt it to a randomized algorithm to get the thing that we want. Okay, so the main insight, remember that what we said is we wanted to avoid forgetting the history, and we want to use the history. And the idea is when an expert makes a mistake, we're not going to completely disqualify them. We're just going to lower their weight. Okay, so the weight of an expert is going to record all of the mistakes they've done in the past and sort of count how many mistakes they've done. So the algorithm is, we start with all experts having weight 1. At every round, we predict based on the weighted majority. So now we look at the total weight of experts saying yes, the total weight of experts saying no, and we go with the higher weight. And if an expert makes a mistake, we penalize it by cutting its weight in half. Okay, so we remove half of its current weight. So for example, if it had weight 1/4, it becomes 1/8, 1/8. Okay, so here's an example of this algorithm. So in round 1, these light blue lines are going to show us the weights. So our 4 experts are going to start with weight 1. And okay, and the total weight, actually, yeah, they should say round instead of weight. Okay, so in round 1, everybody has weight 1. And then we get the predictions. So expert 1 says down, expert 2 says up, and Charlie says up as well. The algorithm predicts based on the majority. So here we have a total weight of 3 for up, a total weight of 1 for down. So we go with the majority, which says up. So the algorithm says up, and the truth is up. So we got it right. What we're going to do is penalize the one expert who got it wrong by cutting its weight in half. Okay, but just let's just take a look at this illustration. So what we had is 3/4 of the total weight was right, 1/4 of the total weight was wrong. And what we're going to do is take the one expert who had this total weight and cut this weight in 1/2. We penalize all of these experts. So now the guy who made the mistake before has weight 1/2, and everybody has weight 1 like before because they got the previous guess right. And in round 2, so in round 2, expert 1 says up, expert 2 says up, 3 and Charlie say down. So now the algorithm looks at these predictions. There's a total weight of 1.5 for up, a total weight of 2 for down, so the algorithm goes with down, right? But then the truth is again up. So now we as the algorithm actually made a mistake, and we're going to penalize the experts who made the mistake. So now the this 1/2 weight, which is actually more than half of the total weight in the system right now, got it wrong, so we're going to cut this weight in half. Right, so these experts who made the mistake before, now their weight is cut to 1/2, and now our total weight is this large. Okay, so if the total weight in the system is going down over time, and one thing that I already want you to notice is that when we make a mistake, the total weight in the system goes down by a lot. And that's what we're going to use in order to derive the bound. Okay. Any questions about how this algorithm works? Okay, so let's analyze this algorithm. And like I said, I think this is a very simple and really beautiful analysis. So let's denote by capital M the total number of mistakes that we've made so far, let's say over T rounds. And small m is going to be the total number of mistakes of the best expert so far. So this is what we're trying to compete with, and what we want to say is capital M is not too far from small m. Now, capital W is going to be the total weight in the system, which starts at n and goes down when experts make mistakes. Okay, now the crucial point, which is what we saw in the illustration, is that every time we make a mistake, the total weight in the system drops by at least 25%. Okay, so every time we make a mistake, it means at least half of the total weight in the system voted for the wrong answer, right? And then all of the experts, all of that total weight of at least 1/2 gets cut by half. So the total weight in the system goes down by at least 1/4 of what it was before. So that means that after we've made capital M mistakes, the total weight in the system can be at most the initial weight, which is n, times 3/4 to the power of m. Right? Every time we make a mistake, the weight becomes at most 3/4 of what it was before. So after m mistakes, it's going to be the starting weight of n times 3/4 to the power of the number of mistakes we made, which is capital M. Okay, so this gives us a bound on the total weight of all experts in the system at the end of the process, after T rounds. Now, what's the weight of the best expert? Well, every time this expert makes a mistake, its weight gets cut by 1/2. So after small m mistakes, its weight is going to be 1/2 to the power of m. It starts with 1, every time gets cut by 1/2 to the power of m. Now here's the beautiful thing. So we have these two things. Now all we're saying here is the weight of the best expert is at most the total weight in the system. Okay, so it's like this very loose bound. We just say, okay, of course, the best expert, his weight can't be more than the total for all of the experts in the system. So the weight of the best expert is at most the total weight in the system, is at most W, which is at most this. Then by rearranging, we get this inequality. And by taking log base 4/3, we get that capital M is at most 2.5, it's even like 2.4, times m plus log m. Okay, the 2.5 is roughly log base 4/3 of 2. So you get this thing. So this is much, much better than before, right? Before what we had is when we said, take this mistake-bound algorithm, which makes at most log n mistakes for every mistake of the best expert, and run it iteratively in rounds. So what we got there was capital M is at most log n times m. What we're getting here is capital M is at most the small constant, 2.5, times small m, plus an additional relatively small additive term of 2.5 times log n. Now notice that log n is a constant here, so it's the total number of actions available to us. So we're not that worried about this thing. What we are worried about is that we're making 2.5 as many mistakes as the best expert in hindsight, so that doesn't actually give us a no regret bound. Right? When we take the ratio, then we're going to get, so we're not going to get a no regret bound. So what I want to do is to use this approach in order to get a no regret bound, and we're going to do that by using randomization. But so the analysis will be an extension of this kind of analysis using the same ideas. So let me first ask you guys, is everybody okay with this simpler analysis before we move on? Okay. Cool. So the idea is, I think, a very natural one. So really what we want to do is use the same kind of ideas, but introduce randomness. And that leads us to this randomized weighted majority algorithm. So like before, we're going to start with all experts having a weight of 1. But now there are going to be two key differences. The first key difference is that we're going to, instead of going with the majority deterministically, we're going to predict proportionally to the weights. So we're going to look at the total weight of plus, which is W plus, the total weight of minus, which is W minus, and then we'll predict plus with probability W plus divided by their sum, and we'll predict minus with probability W minus divided by their sum. Okay, so we just go with every fraction with probability proportional to its total weight. So that's one idea. Okay, so instead of like before saying we just go with the majority deterministically, and we said that would be bad because deterministic algorithms have no hope of getting no regret bounds, now we do things in a randomized way. So at least now we have hope of getting a no regret algorithm. Now the second idea is that before we were saying if an expert makes a mistake, just cut its weight in half, which seems pretty brutal. So now we're saying let's penalize mistakes by removing an epsilon fraction of the weight of the expert, with epsilon to be determined later. Okay, so we won't be as brutal as before, but we will sort of adjust your weight as time goes on, depending on the number of mistakes that you make. Yeah?
This says an adversary do the action after the algorithm picks the action or no?
Yes, excellent. So that's going back to our discussion before. So now the setting is at every round, the adversary knows our distribution. So it knows the current weights. It knows the distribution with which we'll choose an action. Then based on that information, it chooses losses, costs, and then our randomization is realized. Okay? So you can think of it as like we are committing to a randomized strategy in each round, and then the adversary is best responding. And we'll go back to this viewpoint later, but in this sense, it's like a Stackelberg game where we get to commit to a randomized strategy. The adversary sees the randomization, but doesn't see the instantiation, and then best responds, or like gives a bad loss vector. Okay, so just to give you some intuition, I don't think this is the full picture, but just to give you some intuition of why this might help us. So before, the worst case for us was the case where the weights are split almost 1/2 between getting the right answer and the wrong answer. But there's weight, it's hard to see in the picture, there's weight slightly larger for the wrong answer. So this means that on the one hand, we make a mistake. There's a majority of weight for the wrong answer. On the other hand, we don't get to cut that much weight. So we only get to cut 25% of the weight. So that's a worst case for us. Now, we actually have an almost 50% chance of getting the right answer. Right? So here, when it's like 50-50 in terms of weights, we actually have a pretty decent chance of getting the right answer in this bad case. So this really smooths out the bad case. On the other hand, we could be losing in a case where, if there's like 90% right answer, 10% wrong answer, then before we were definitely getting the answer right. Now we actually do have a chance to make a mistake, but it's a pretty small chance. It's only 10%. And somehow, these things sort of balance out. I mean, of course, it's going to be worse for us if it's like 51% right, 52% wrong, but 49% wrong, but things sort of work out. Okay, so here's the analysis of this algorithm. So I want to convince you that this actually gives no regret guarantees. And the idea is going to be very similar to what we had before, but with a slightly more refined analysis. Let's see. So at time t, we have a fraction that we denote by f sub t of experts who made a mistake. Now this is something that we know in hindsight. So we look at the end of the process. We look at like what the algorithm did in each round, and what the adversary chose, and we look at what fraction of weight of experts at the time made a mistake. Okay, so this we can determine in hindsight. Now, in every round, if there was an ft fraction of weight on experts who made a mistake, we had the probability of ft of following these wrong experts, and therefore we had the probability of ft of making a mistake. And in addition, regardless of whether we made a mistake or not, right, we always remove an epsilon times ft fraction of the total weight. Because for every wrong expert, we remove an epsilon fraction of their weight. If the total weight of these guys is an ft fraction, we would end up removing an epsilon times ft fraction of the total weight. So the crucial thing here, and this we'll come back to this in a few minutes, is that our expected, so the fraction of the total weight that we remove is epsilon times our expected cost in each round. Right, so we have like our expected cost is going to be ft. We remove an epsilon times ft fraction of the total weight. So we have this relation between the two things, which is really the crucial thing here. Now let's see why this helps us. So like before, let's look at the weight at the end of the process, W final. So that's going to be the starting weight of n. And then we said in every round, we remove an epsilon times ft fraction of the total weight. So that means we take the previous weight, we multiply it by 1 minus epsilon times f of t. That's a fraction of weight we have remaining. And after all of the rounds, we have to multiply by this fraction that we removed every time. So we end up with the initial weight times this product of all of the fractions that we removed. Okay, so again, this is the initial total weight. Every expert has weight 1. And this is like the, just multiplying every time because we remove some fraction of the weight. So that's the final weight. Let's just take the ln of this. So we get, ln of a product is the sum of lns. So this is ln n plus ln of this thing. Again, we have a product. So it's the sum over t of ln epsilon minus 1 minus epsilon f of t. Now, we're going to use an inequality that I'll convince you of on the next slide, which is for every x, ln of 1 minus x is at most minus x. So that helps us replace these ln of 1 minus epsilon ft with just minus epsilon ft. So we can say this sum is at most this sum. Okay, by just using this inequality where x equals epsilon times ft. And now the beautiful thing is, okay, so we keep the ln n, but what is this? This is our expected number of mistakes. Right? Because on every round t, we're saying, we're following the wrong experts with probability ft. So our expected number of mistakes is the sum over t of ft, which is capital M. Okay, there's something really magical going on here, I think. Part of what's playing in our favor, it's sort of slightly confusing because, the question of whether, the question of how much the weight goes down, that's independent of whether we made a mistake or not, right? Because the experts who made the mistake, they're going to lose their weight regardless of whether we chose to follow them or not. So that's why, that's why you don't have any funny stuff happening in this kind of thing. On the other hand, even though things depend on each other ultimately, because of linearity of expectation, you basically get this thing where we can just look at our probability of making a mistake at every round. When we sum over all of these probabilities, that's going to be our expected number of mistakes. Okay, so even though all of these things depend on each other, maybe this is a bit too subtle, but for those of you who are thinking about this, like even though everything depends on each other, and you might worry there's some funny business going on, to go from this to this, to say this is our expected number of mistakes, we're just using linearity of expectation to say our expected number of mistakes in every round is ft, and then when we sum over all of these expectations, that's the expected total number of mistakes that we make. Okay, so that sort of gives us the equality between this thing and converting the sum of ft's to our expected number of mistakes m. So I just convinced you that ln of 1 minus x is at most minus x. This is the proof. Okay. So what did we get? Oh, so one more point. What is the weight of the best expert? Okay, so this W best, the weight of the best expert. Remember that expert started from a weight of 1. Every time that it makes a mistake, we multiply its weight by 1 minus epsilon. We remove an epsilon fraction of the weight. So after making small m mistakes, its weight is going to be 1 minus epsilon to the power of m, which is kind of what we had before. Before it was 1/2 to the power of m. Now we just say we remove an epsilon fraction with epsilon to be determined on the next point. Okay, so now so what did we get? We got an expression for an inequality for the ln of the final weight. We got an inequality for the weight of the best expert. And now what we just say is the weight of all experts at the end is at least the weight of the best expert, which is exactly the idea that we had before. Therefore, if we take ln here and ln here, we still have this inequality. Ln of W final, we said on the previous slide, is at most ln n minus epsilon capital M. That's what we proved on the previous slide. And here we just said ln of the weight of the best expert is exactly m times ln 1 minus epsilon. So now we have this inequality that says it's an expression that connects m, small m, capital M, epsilon, and n. So now what we want to do is derive a bound on m, and we still have to set epsilon. So essentially what you do is set epsilon to balance things, and when you actually do the calculation, the optimal value for epsilon is square root of ln n over m. And if you solve this and extract m as a function of all of the other stuff, what you get is that capital M, or total number of mistakes, is at most small m, plus an additional additive term of square root of m times ln n. Okay, so that's just doing the calculation to extract m and plugging in this value of epsilon. Now, because m is at most, the number of mistakes made by the best expert is at most the number of rounds t, then what we got is that our number of mistakes is at most the number of mistakes of the best expert in hindsight, plus this additive term of 2 times square root of t times ln n. Okay, so this says our total regret, the difference between how many mistakes we made and the best expert, this difference is at most this term. And now we have a no regret algorithm, because this term is sublinear in t. So when we divide by t, we get an expression. Remember, we think of n as a constant. We get an expression that goes to 0 as t goes to infinity. Any questions about this? Alex?
So if we do, if we substitute 2 to epsilon in the deterministic algorithm, what we will get?
Yeah, so you definitely wouldn't get a no regret algorithm, because we know you can't get a no regret algorithm with deterministic algorithm.
Can you
Yeah.
make that constant?
Yeah.
And like very small, like I don't know, 1.01.
Yeah. Yeah, you can definitely get a better constant. Yeah, it's a good question. I mean, I don't know what's the optimal trade-off there. So we know it's not going to be, we know we're going to have a multiplicative constant. I'm not sure what the best one is. Roger?
Wait, so why is 3 greater than the square root of t ln n? Is m like what our best case scenario would be? And why is that?
Right, so you mean small m?
Yeah.
Right, so we're saying, regret is defined by our cost versus the best expert in hindsight. The best, so small m is defined to be the cost of the best expert in hindsight. It's the number of mistakes made by the best expert.
Oh.
Right, so if you look at like our cost minus m, what this is saying is that's at most this term. Okay, so that's our regret. And then to talk about average regret, we have to divide this term by t. Matthew?
So for in analysis, we can say epsilon is something and assume like small m is just a variable, but in actually implementing the algorithm, how do you choose epsilon and what m will be?
Excellent, that's a very good question. So what Matthew is asking is, here I really cheated by saying, okay, I sort of know in advance, right? I have to set epsilon because throughout my algorithm, I remove an epsilon fraction of the weight in each point. So I'm saying, okay, what will I do? I'm going to set epsilon in a way that depends, I know what n is, but I don't know what the small m is. That's a number of mistakes that I'm going, the best expert is going to make. So what Matthew is saying is, I cheated, like I have no way of actually running this algorithm. That's a great point. There's a very standard trick to get around this. It's called guessing and doubling. So what you essentially do is you start by guessing, small m, just set it to something. And then when you find out that you're wrong, so so every expert exceeded that number of mistakes, then you double your guess for small m. Okay, so every time, like epsilon, the epsilon that you use right now will be defined by your current guess for small m. And what you do is you just update your guess for small m as you find out that it's wrong. And you basically get the same bound. So it's just going to be like a constant difference. Yeah, and it's something that, this idea of guessing and doubling is something that's useful like in many areas of algorithms. So it's basically the same analysis.
So just to get that straight, so it's like as you go along in the algorithm, you start with epsilon x, and then once small m exceeds at some step the value that you guessed, then you double.
Yes, exactly. So and the idea is, so at every point, as time goes on, your value of epsilon is getting smaller and smaller, right? And the idea is, so far you sort of got some guarantees that dependent on some epsilon that was larger than what you would need for the analysis, but as time goes on, that stuff sort of cancels out with the better guarantees you're getting in the current phase. So then things, but you basically get the same bound ultimately. Okay. Yeah.
So this is like the binary case where it's 0 or 1.
Yes.
What happens in the continuous?
Excellent. That's the next slide. Any other questions about this slide before we answer Ankush's question? Okay, great. So let's answer that question. So now we're going back to the more general case. And I'm not going to analyze it, just to argue in a hand-wavy fashion that it's sort of the same. So now every expert is an action with cost in 0, 1, like before. And, the way we think, so let's rethink about randomized weighted majority. So before we said, let's look at the total weight of the pluses and the total weight of the minuses and go with the majority. But a different way to think about it is choose a random expert with probability proportional to its weight and do what it says, that particular expert. Right? That would give you the same distribution over answers, over what you do. So here we're just doing that directly. Like here we can't say, it's not that there are only two choices, so we can't do the same thing as before, but we can take that interpretation and just say what we'll do is choose expert I with probability its weight divided by the total weight right now. And then what we'll do is we'll update the weights, but also in a way that depends on the cost. So instead of, before we said, oh, the cost is either 0, you don't lose weight, or 1, you lose an epsilon fraction. Now the fraction that you lose is going to depend on your cost times epsilon. So if your cost was 0, like before, you don't lose anything. If your cost is 1, like before, you lose an epsilon fraction. But if it's 1/2, you lose an epsilon over 2 fraction. So that's, I think that's the most, a very natural way to generalize what we just did to this more general setting. Now, the crucial thing is, and that's why I highlighted this one point before, our expected cost now is going to be the sum over j of Cj times Wj divided by the total weight, because this is our probability of choosing expert j, and if we do, then we get a cost of Cj. Now, the fraction of weight to be removed is this fraction, okay, which is the same idea. So what we get is, like before, the fraction of weight we remove is epsilon times our cost. So that relation that we had before and was crucial still holds in this more general setting, and that's why sort of the same proof goes through. Okay. Excellent. Okay, so that's what I wanted to say about no regret learning. So now we're switching gears and going back to the min-max theorem. Okay, so all of this work that we've done over the last hour was building up towards this last kind of guarantee of like we can get a no regret learning algorithm with this regret. And now I want to use this in order to prove the min-max theorem. And this is, I think, a really beautiful proof. Okay, so min-max theorem, again, we want to show that if the row player commits and then the column player gets to respond, what the row player can guarantee is the same as what the column player can guarantee if they commit and then the row player responds. So let's suppose for contradiction that we have two values VC and VR, where VC is what the column player gets if he commits first, and VR is what the row player gets if he commits first. And of course, VC is greater than VR because remember, the column player wants the value to be as low as possible. So if he commits first and then the row player responds, the column player is at a disadvantage. If the row player commits first and then he can get VR and the column player responds, then the column player is at an advantage. So it's pretty obvious that VC is at least VR. What the min-max theorem says is that VC equals VR, and our contradiction assumption is that VC is strictly greater than VR. Okay, so we don't need to worry about the inequality in the opposite direction. That's pretty obvious. But what we are worrying about is the inequality in this direction, where VC is strictly greater than VR. So again, to make sure we're on the same page, so VC is like if the column player commits first, there is a row that guarantees the row player at least VC, so that's what the column player can guarantee by committing first. And VR is what the row player can guarantee by committing first. So now we can scale the matrix so that the payoffs to the row player, we can think of them as costs and 0, 1 like before. So the idea is, if we sort of translate the payoffs, then the difference between these two things will be exactly the same as before. And now if we scale the payoffs to be in -1, 0, then it's just going to scale the difference. But if we had some difference before, we're still going to have some difference between VC and VR. Okay, so this just says, it's sort of without loss of generality to assume that in this game, the costs to the row player are in -1, 0 to fit the setting that we talked about. And let's say, if VC is strictly greater than VR, let's just define delta to be the difference between them. Okay, so here's the beautiful argument. So what we'll do is imagine the following game where the row player and the column player just play this game repeatedly. Okay, so we have like T rounds, and we're going to play this game again and again. And the way we play it is the row player has to commit to a randomized strategy, and then the column player responds. Okay, so we're basically playing a repeated Stackelberg game with the row player committing every time and the column player responding. And this game is the game that we just had on the previous slide. Okay, same game. We play it for T rounds. So what we'll do is we'll let the row player play according to randomized weighted majority. All right, so the row player runs that algorithm. It tells them which distribution over rows, over actions to play right now, and then he plays that, and then the column player best responds to that strategy. Okay, so this is the cool idea. So the randomized weighted majority gives the row player a strategy that he can play in this game. Now, what would happen when we play this game? So first of all, because of the guarantee that we just derived for randomized weighted majority, we have this regret bound that what the algorithm gets is at least the best row in hindsight minus that additive thing that we had before. Okay, that's what we worked the whole lecture to prove. Okay, so this we have, great. Now, what is the algorithm getting? So remember that VR is the best value the algorithm can guarantee to himself. And we actually told them not to play the strategy that necessarily guarantees VR, but some other strategy defined by randomized weighted majority. So and then the column player is best responding. So of course, what the row player is getting can't be more than what he could guarantee to himself if he played the best possible thing for him on every round. So on every round, he can get at most VR. And we play this for T rounds. So after T rounds, you can get at most T times VR. Okay. Okay, now the final point is a bit trickier. So now we want to argue that the best row in hindsight gives us at least T times VC. Okay, so if we could now look at what the adversary did in every T rounds, in all of the T rounds, and the row player gets to choose a strategy, the best one would actually have this guarantee. So why is that? So let's think about it this way. So let's say that in round 1, or like in round T, the adversary plays some strategy. Let's call it SJT. Okay, this is the strategy. Let's just call it ST to make it like a bit nicer. Okay, ST. Okay, so this, we're looking in hindsight, so we know exactly what the adversary played in every round. And now we're going to define a strategy, a mixed strategy for player 1, for the row player. So let's define the strategy X that plays each ST with probability 1 over T. Okay, so there could be multiplicities here. If the adversary played the same strategy multiple times, the probabilities add up. Okay, so it could be the case that S1 is equal to S5, then that strategy will be played with probability 2 over T. Okay? So this defines a mixed strategy X. Right, now, right, so now what we want to think about is what would happen if our algorithm played this mixed strategy X, right? So what would happen? What would be the utility to the algorithm? Okay, so the utility when the algorithm plays, let's actually call it Y to be more consistent with past notation. So let's call this Y. And what I'll do is, let me define X actually. So this is Y. And the way I'll define X is going to be the best response to Y. Okay, so this thing defines a strategy for the column player, okay, which, like we said, is 1 over T times what they played in round T. Okay, sorry for the mix-up. This is the strategy for the column player. what we'll do is for the role player, we'll choose the best response X to the strategy Y. So role player plays best response X to the strategy Y. Okay? Good. So now let's think about what would be the utility to player one, to the role player, by playing X against Y. So the utility to 1 for playing X against Y, so that's going to be 1 over T times the utility to 1 for playing X against S1, plus 1 over T times the utility to 1 for playing X against ST. Okay, that's the expected utility to 1 when playing against this randomized strategy. Now, what is the utility if we chose X and played it in every round of this game? What would be the utility to 1? Right? In this repeated game, what would 1 get if they played X in every round? So in round 1, they would get this thing. In round 2, they would get U1 of X versus S2, and so on. In round T, they would get the utility to 1 of X versus ST. Okay, so if we played strategy X in every round, we would get this sum of utilities. Now, the claim is this thing, what we have here, can be, has to be at least VC, right? The reason is that here the column player is committing to some strategy, this mixed strategy Y, and the role player is best responding to that strategy. So the role player will be able to get at least what they could get if the column player committed to the best strategy for them. Right? So what we're saying is, this utility of X versus Y, this has to be at least VC. Okay, it's at least what the column player can guarantee to himself by playing the best strategy for them. Here they're playing Y instead. And what we're saying is, what we would be getting when we play X again and again in this game, this strategy in hindsight, would be the same sum without dividing by 1 over T. So what we're able to get is at least T times VC. Okay, so hopefully this was clear. This is the proof for this inequality. If it was unclear, and I again apologize for the confusion, it could be a nice exercise to do at home. But again, what we proved is that the best row in hindsight is at least T times VC. And now we just need to put these inequalities together. So what we get is T times VR is at least the algorithm. The algorithm is at least the best row in hindsight minus this additive term. The best row in hindsight is at least T times VC. So putting these inequalities together, we get T times VR is at least T times VC minus 2 times square root of T log n. So now what we do is we just move T times VR to this side and this thing to the other side. We get T times VC minus VR, which is T times delta. So you just get that delta T is smaller or equal than our additive term. But this is something that is linear in T, and this is something that grows like square root of T. So for large enough T, this inequality can't be true. Okay? So this is not an easy proof, but again, I think the connection here is really beautiful. Right? So what we said is, we did all of this work to prove a regret bound for that randomized weighted majority. In this game, we let player one play that algorithm. We used the guarantee that we got here. Then we used, simple and slightly less simple arguments to get these two inequalities. And then by just putting them together, we get a proof for the min-max theorem. Okay, so this sort of says there is a fundamental connection between these two things. And like I said, there is quite a bit of work in the intersection of learning theory and game theory that talks about learning in games. And this kind of insight is the basis for all of that work for making that connection. Okay, that's it for today. See you on Wednesday.